participants, please feel free to type in your questions even during the presentation, and we will be asking those questions towards the end. You could either type it in chat or you could type it in the section where you could ask questions. So over to you, Jacob.
All right, great. Well, thanks for having me. As stated, my name is Jacob Holcomb. I'm a security analyst at Independent Security Evaluators, and today I'm going to be talking to you about the exploitation of Internet of Things. So who am I? Jacob Holcomb. I specialize in application and network security. I absolutely love exploit research and development. I like, dissecting someone else's code, finding vulnerabilities in the code, and just, I guess, making it better. And why do I do this? Well, security is important. It isn't a niche market, as some like to say. It really is something that needs to be taken seriously at all levels by all types of consumers. Anybody from, your home user all the way to your Fortune 50 enterprise. So really quick about ISE, Independent Security Evaluators. This company is comprised of a bunch of ethical hackers and computer scientists. Above all, each one of our employees are a unique individual. We all bring, something to the table that allows us to better ourselves and the company professionally. Our customers are Fortune 500 enterprises, and we are heavily weighted towards the entertainment, security software, and healthcare industries. And our perspective is white box. And really quick, a white box is more of a vulnerability assessment. It gets into the low-level, gritty details of a system and its architecture, and basically uncovers fundamental design deficiencies that would allow an attacker to exploit them for profit. Whereas a black box penetration test is more of a shadowed approach in that testers or researchers will attempt to break an application without actually having a firm understanding of its inner workings. So really quick, why is Internet of Things security important? Well, from the research that ISE has performed, we've determined that 100% of IoT systems were vulnerable to exploitation. Now, specifically, we looked at storage systems and network routers. And other researchers have proved that other embedded systems, such as medical devices and like network cameras, for example, contain egregious vulnerabilities as well. Routers and storage systems are basically two key components to, I guess, really any network. You're going to have a perimeter device, which is most likely some form of router or firewall, which essentially is the primary point of egress and ingress into your network. And then your storage system, whether it's a file server, a storage area network, and network attached storage, you have some form of central repository on your network that is responsible for maintaining all of your company's files and data. Internet of Things systems can and are being mass exploited. As demonstrated several times throughout the past year and a half or 2 years, there have been large-scale attacks against networks such as Microsoft and Sony, where compromised routers, for instance, brought down the entire network and essentially left it in an inoperable state. There were some other examples which we'll discuss later in the presentation. Every day, new devices are becoming connected to the internet and transmitting some form of data. I mean, for instance, cars are now becoming connected to the internet, coffee makers, refrigerators, as we stated, storage systems and routers, just really any electronic you can think of is evolving in such a way that there is an always-on data connection. And once a system is connected to the internet and able to participate in remote correspondence, you're opening a new can of worms. You're essentially increasing the attack surface, which potentially could put both that system and the data assets it's protecting at risk. It's a serious problem. So Gartner says the Internet of Things install base will grow to 26 billion units by 2020. As we all know, technology is growing at an exponential rate, and the amount of systems that you have in your home, business, home office, whatever it may be, are being connected to the Internet and allowing us to do things that we weren't able to do, a decade ago. So IOC, Internet of Things research. So as I mentioned, this company has evaluated Soho routers extensively. This past year, I really focused on network storage systems, and I gave a presentation at Black Hat USA and Black Hat Europe where I discussed the exploitation of these systems and also demonstrated a network worm, which is a self-replicating piece of malware that went out and fingerprinted IP addresses to determine if they were a vulnerable storage system, and if they were, it exploited them. And then, hospital systems and infrastructure. Right now, we're working on a report. It's a research project that kind of focuses on the insecurities of the hospital, both kind of a holistic, topology approach to where are the weaknesses in the hospital's defense, and then also we're looking at some of the equipment utilized by a hospital, such as Internet of Things medical devices. If you're curious about any of the research that is listed on the slide, you can visit this URL where we have a bunch of case studies, white papers, blog posts, and things of that nature. So Hopelessly Broken. This was a contest that we hosted with the EFF at DEF CON 22 and some other conferences listed below. And this contest was geared toward increasing awareness of users and both manufacturers. And our goal was to allow a bunch of like-minded hackers to attempt to exploit these systems for cash and prizes. And in essence, we were notifying the vendors and making more secure products. So the topics we'll be discussing today are the risks of networking equipment, threat modeling and testing methodologies, the remediation of vulnerabilities and security design principles. And then once we've talked about all that, we'll kind of briefly recap, how an organization may integrate Internet of Things devices into their network. So the risks. Well, these systems contain large attack surfaces. Every time you introduce a new piece of functionality to a device, you're expanding the surface that can be attacked. Internet of Things devices have a plethora of network services and functionality with the goal of making life easier for the end user. Well, with increased ease of use, you're most likely decreasing the level of security. And that allows an attacker to, leverage some of the functionality offered by these systems in a way that can ultimately lead to their compromise. A lot of operating systems today, whether they run on Internet of Things devices or on your desktop or laptop, are insecure by default. And that's normally directly correlated to the manufacturer wanting the setup process to be as easy as possible. They essentially want the path of least resistance for their users, so they can pretty much plug in the device, turn it on, and be ready to go. Now that means a lot of insecure services, encryption, and things of that nature are either in use or aren't leveraged, and that allows for, again, a malicious adversary to utilize the device in an unintended way. Threat modeling. So before you can really perform any assessment of a product, you really kind of need to understand issues that could be present in your design and the types of assets that are going to be protected by this device or piece of software. So threat modeling allows a software development team to identify issues they may encounter in the development process early on, and it will then allow them to, kind of remediate or resolve these vulnerabilities in a way that isn't quite as expensive as if they were to have been found once the code was already in production. Threat modeling gives you the ability to thoroughly understand your system and how it operates at all levels with different user types and all of the assets that the system interacts with, whether it's an asset that the system stores directly or it's an asset that the system is protecting. An example would be a router. Well, a router may not hold any concrete or physical assets, but it is the single point of ingress and egress into your network, as I've stated, and by virtue of that, assets will flow in and out of that device. So you would want your router to be secure because if it was compromised, an attacker may be able to snatch up your assets as he controls an intermediary point between you and the destination. And finally, threat modeling, it should be a core component of any software development lifecycle process. It'll keep your costs down and hopefully ensure that you have as few vulnerabilities as possible. So when you do threat modeling correctly, it empowers you and your company. You have a firm understanding of your project scope, what you're intending to do with your software or product. You're then able to thoroughly model your system and have an understanding of what you want it to do and what it is or isn't doing. You can identify all of the assets that the system protects. You can identify the threat actors who would be the individuals seeking to do your assets harm. And then you can identify vulnerabilities. And the vulnerabilities are essentially the weaknesses that threat actors will exploit to gain access to your assets. So once you have all these things kind of lined up and you have an understanding of your system, you can start to quantify the risk and basically rate each vulnerability and threat with a likelihood of exploitation or a likelihood that the vulnerability or that a specific threat actor may exploit a vulnerability. And understanding this and all of the people or all the threat actors that would want to attack you, you're able to develop a well-rounded security response plan. And this would allow you to adequately respond to an incident should one occur. So testing methodology.
So Jacob, I had a question.
Oh yeah, sure.
So basically, even for, say, conventional penetration testing for an application, we use more or less similar methodology. So it will be great to know like how the IoT is different or what are the things which you see them differently in that context and stuff like that. So that will be wonderful to know.
Sure. So honestly, my opinion is that threat modeling, really the process is going to be the same for whatever type of application or hardware product you're assessing. Now the individual components like the assets and threats and vulnerabilities may differ, but the approach is going to be the same. One thing that's different about Internet of Things devices versus, let's say, a Microsoft Windows laptop is that Microsoft Windows supports technologies that the enterprise can leverage to, gain fine control over the system, whereas these IoT devices may not. So you may not have granular control over security mechanisms, which can make it harder to manage. So I guess some of the differences in the threat modeling process would be around some of the internal access controls. Okay, so testing methodology. Before you can get into breaking these systems and discovering the vulnerabilities that may exist, you have to have a proper threat model. Once that threat model has been nailed out, like we just discussed, we're able to actually get into some of the nitty-gritty hacking. And there are several stages here to the testing methodology that we employ during our testing. First is the information gathering. Now this is slightly different than a black box penetration test in the sense that black box penetration test, the information gathering stage will be used to gather as much information as you can about an organization. When we're assessing a IoT device, we look at the picture slightly differently. And what we're going to do here is try and gather as much information about the default configuration of the device as possible. You know, we want to know all of the administrative interfaces that are available, Telnet, SSH, web-based, what are the default credentials, the wireless LAN or LAN settings, you know, what is the SSID, what type of wireless encryption is employed, what is the layer 3 IP range of the device, which can be beneficial to one testing and performing client-side attacks, and then what network services are running on the system and what are their default settings. Once we've gathered this information, we move on to scanning and enumeration. And this is essentially a step where an attacker will identify active hosts and all of the TCP and UDP ports that are open. Once we know all the ports that are open, we can attempt to identify the services and their versions operating on each port. So scanning and enumeration continued. Port scanning is normally done with a tool called Nmap. This is a very famous tool. It's very robust. A lot of time you can just roll your own port scanner, but there really isn't a point. This is a great tool that can be used to identify all TCP and UDP ports and then also attempt to fingerprint them for you. Now, the results of this tool aren't guaranteed to be 100% accurate, so you may have to perform some level of manual investigation. And tools that utilize sockets, such as Netcat, are great for this, or just rolling your own Python, C, or shell script code. But what you'll do is you'll connect to a specific port that you identified from your Nmap output and attempt to see if it is the same type of server or service that was reported in Nmap, which you can see under the banner grab heading here. All right. Once you have that.
So one question which I wanted to ask was that the Internet of Things devices, sometimes the interfacing might be very different compared to the standard web apps or the network devices. So, or do you see any interfacing challenges, like some of the Internet of Things, I mean, it could be something in your refrigerator or your light bulb or even your car, right? And this year there were demonstrations of how you could hack a car, even freeze the steering wheel while you are on the move. So what I meant to ask was that what are the interfacing difficulties which you might have with all these IoT devices before which you could, I mean, without doing which you can't do the port scan? Are there some of those challenges?
Yeah, sure. I mean, so it's really going to depend on how the device is connected. I guess now we're starting to make the assumption that, you know, every device that is classified as an IoT, Internet of Things device, has some level of network connectivity, whether it's wired or wireless, you know, or both. But there is some way that the device is, you know, always connected to a network. And by virtue of that, you should be able to interface with it incredibly easily, as long as there aren't any intermediary, you know, firewalls or other systems preventing you from communicating with it. Now, if you wanted to like look at a car computer, for instance, you know, within a car that does not have Wi-Fi, you're getting more into the physical type of attacks, and you aren't necessarily going to be performing this network scanning and enumeration. Your testing will be different.
Probably it will not be right to call it IoT, right? Because that's not connected as such with the Internet always.
Correct.
Or
exactly.
are there some connections?
Yep, that is definitely a key differentiator between devices that are IoT and devices that are not.
Okay, and maybe there could be some components over there which could be IoT, which could be connected with the internet, which you can use a multi-stage attack to further venture into. So,
absolutely. Yep.
Okay. So typically what you are saying is for the common IoT devices, the interfacing is not a challenge.
Correct. That's correct. All right. So assuming you're able to interface with an IoT device, it has network connectivity, you're going to want to analyze the services that run on the device. So if you discovered a web server that was open, you're going to want to look at the web application and try and understand it, determine what its use is. You'll want to analyze every other service that you see running on the device, whether it's an FTP, SMTP, SMB, or HTTP server. If source code is available, you definitely want to perform a static code review. This will allow you to, I don't like saying this because I think it is inaccurate to some level, but a static source code review allows you to get as close as you can to 100% code coverage compared to a dynamic analysis approach. And dynamic analysis is fuzzing. That's essentially where you would connect to these network services and send them a plethora of peculiar input with an expectation of the service crashing or stop responding to your requests. So if you identified a web application, you need to understand the application. You need to know the programming languages that are used both server and client side, the protocols and APIs that are used. And some great tools for performing these tests are web proxies, a JavaScript debugger, an HTML inspection tool, which you could use the built-in browser developer tools, or a Firefox add-on named Firebug, a web crawler, which essentially crawls a web page, finds all the links on the page, and then continues that process, and Python, which is a great scripting language that allows you to automate a lot of this testing in a way that makes it less cumbersome for you. So here is a picture of Burp Suite on the left, which is, again, the web application proxy, which allows you to intercept server requests and responses that are made by the application server. And then Firebug on the right, which here we're just inspecting the HTML of the page. So analyzing network servers. Once you've identified all the services, you want to know if the service is enforcing the authentication, the type, if it is, whether or not no credentials or weak credentials are in use, or even better, anonymous access or misconfigurations. The protocol is very important. You need to understand what it is. Is it standard? Is it something like HTTP, FTP, where there's a clearly defined RFC you can go refer to? Is it custom? Was it rolled in a way that requires some level of reverse engineering before you can speak it and communicate with this server? And then finally, is encryption used? SSL or TLS. If SSH is running, is it using AES or triple DES? So you just want to gather more and more information while bettering your understanding of the system. I mentioned this already, static code analysis. If you're reviewing a piece of software or a system that is running software, which all systems do, if the source code is available to you, get it. You definitely want to review it, whether it is a pure manual assessment or you're running static analysis tools to attempt to identify vulnerabilities. With source code, you can look for common things such as logic flaws. Authentication and authorization are huge. We see these a lot in APIs where there are privileged API calls, but they aren't properly enforcing authorization, which results in a lower privileged user performing an privileged action. An example would be a regular user adding an administrator user to the system. Now, only admins should be able to do that, but with these types of flaws, lower privileged users are able to do that as well. Functions not performing bounds checking are another thing you should look for. Yes, this is definitely a vulnerability that was exploited in the mid-90s heavily, buffer overflows. You still see them today. They're very prevalent. So you definitely want to look for your typical functions such as stir copy, mem copy, anything that essentially will take user-controlled input and copy it to some space in memory without checking its length. And then backdoors. We won't get into why backdoors exist in these systems, whether they're intentional or left over from development, but backdoors can exist. And if they exist, they are a hole on your network where anybody who is aware of them can then exploit them and use them to gain access to sensitive systems and information you're hoping to protect. So here is some vulnerable code. And this is kind of beneficial to see because it shows why static code analysis is important. So here in the arrow where it says overflow, you can see we have an sprintf call, and it's taking the WAN PPTP username and WAN PPTP password and getting those values and copying them to a buffer. Now buff, BUF, as you can see here, is only 256 bytes. Now those two values, the WAN PPTP username and password, are user controllable. So if a user is able to supply more than 256 bytes of data, it's going to cause an overflow and overwrite adjacent memory. That is a security issue known as a buffer overflow. Additionally, there is a call to system, which is a function that takes essentially a string and it then executes the command string. So if an attacker is able to supply data under PPTP username and password, the attacker could put in operating system commands instead, and once we get down to the system call, the code is going to execute the operating system commands of the attacker's choosing. So within one function here, we have two vulnerabilities that would result in a complete compromise of the system. This is a prime example of poor coding practice. So here is another example. We have more vulnerable code from static analysis to where, again, we have an sprintf command taking two values, apps name and apps flag, and copying them into command. Well, command, as you can see, is only 128 bytes. So just like I said in the previous slide, if an attacker can send more than 128 bytes, he's going to overwrite adjacent memory and cause a crash, which is a security vulnerability. So dynamic analysis, also known as fuzzing. Essentially, all this is you interfacing with a network service and sending it a bunch of peculiar input. Once this input is introduced, it's the attacker's job to observe the application behavior and response and see if you're able to cause abnormal behavior by sending it unexpected data. Some great fuzzers are Spike, the Peach framework, Python again. It's really easy to quickly whip up a custom program that speaks a protocol, and then the Metasploit framework. Once you perform fuzzing and you hopefully find a crash or a service that stopped operating as intended, you're going to need some tools to analyze your fuzzing results. And here you can see I have a picture of a debugger, specifically GDB for the MIPS architecture, and I am debugging a program which contains a bunch of 42s in memory in these various S registers. And the 42s were introduced by an attacker, myself in this case, and I overwrote a bunch of system memory, which allowed me to gain control of the application flow or the program flow. So once we've performed kind of the cursory or initial assessment of the services, we actually need to get into some more low-level details where we'll continue to pry in order to gain access to the system. So we'll perform some reverse engineering on the system binaries, and some great tools for performing reverse engineering are listed here. Some go-tos for sure are strings and grep. They're absolutely fantastic. They're very easy to use, and they yield a lot of information. Some of the more complex tools would be GDB, which is a debugger, IDAPRO, which is a debugger, but also a disassembler. It'll show you the assembler of the binary. And QEMU. QEMU is essentially an emulation platform which allows you to take binaries compiled for a different architecture. An example being MIPS or ARM, and then run them on a x86 or x86-64 architecture through emulation. And while you're emulating them, you could, perform your dynamic analysis on them without having direct access to a system running them. And then exploit development. So reverse engineering tools and techniques. I mentioned strings. Here I'm running strings on a binary called time. And as you can see, it's telling me information about functions that are used, libraries that are used, and some of the strings that are probably passed to functions such as printf, like seconds and hex, microsecond and hex. So this can be beneficial to kind of, gain information about libraries that are used, static strings that are used like constant strings, maybe help you understand the protocol if it happens to be custom and there isn't a standard to refer to, things of that nature. Here is grep. Remember earlier when I mentioned backdoor and looking for backdoors when you perform static code analysis? Well, as you can see here, this arrow is pointing to the word backdoor in a file called broadcom.c. This was actually a function declaration and definition, which you see here, written by Tom Hung in 2012 that introduced a backdoor to a router which allowed an attacker to request a web page with a static string, and it opened an unauthenticated telnet server running as root, which means the attacker can now connect to that telnet server and assume full administrative control. So this backdoor was left in this router and was sitting there ready for anybody to exploit. So when we perform assessments on IoT devices, these are vulnerabilities that are frequently discovered. The most common vulnerability I've discovered in the past year, I would say, would be command injection, where an attacker can introduce operating system-specific commands to the system and have them executed. And then here are some others. Some big ones are cross-site request forgery, which is a web-based client-side attack, memory corruption vulnerabilities such as buffer overflows, and then missing function-level access controls. These are normally your authentication and authorization types of vulnerabilities. So we'll talk about a few of them. The first being cross-site request forgery. And this is an attack that forces unsuspecting users into executing web application commands on a vulnerable website that the end user didn't intend to execute. So the victim first has to be authenticated with the website, which you see depicted by the yellow arrow. They then have to click a malicious link or somehow be directed to an attacker-controlled web page, where the attacker-controlled web page then sends back malicious HTML and JavaScript code to the logged-in user. That code is then rendered in the user's browser and sends a request to the trusted website, which in essence is impersonating the victim. So it is a forged request, and that will carry out a sensitive action such as depositing all of your bank account money into my bank account. Testing for cross-site request forgery is pretty straightforward. There are a couple key things that you want to look for, and the biggest are anti-CSRF tokens. and then HTTP refer checking. So anti-CSRF tokens are normally embedded in the body of an HTML form or included as a GET parameter if it was a GET request. And then refer checking is simply the application checking the refer to ensure that the request it just received came from the trusted website. If an attacker submitted a cross-site request forgery payload, the refer would show the attacker's web server instead of the trusted web server, and that is indicative of a cross-site attack. So countermeasures for cross-site request forgery. Users need to log out of web applications. Assuming that the application was developed correctly, when you click the logout button, your sessions should be terminated and should no longer be allowed to be used in attacks. And do not save your credentials in your browser. Developers, the big things for you are to implement those anti-CSRF tokens we just talked about and refer checking. There are methods in which refer checking can be bypassed, but we're not going to get into that today. And when these two are used in conjunction with each other, it proves to be a pretty robust defense against CSRF attacks. If you're feeling ambitious, every time you're going to perform a state change within your application, require users to re-authenticate. This is basically a tiered approach to preventing cross-site request forgery, and while re-authentication won't thwart CSRF attacks on its own, it definitely adds that extra level of protection to help safeguard users from a malicious cross-site attack. So command injection. This is a great vulnerability. Command injection essentially is equivalent to remote code execution, like a memory corruption bug, but they're usually easier to exploit in that shell code and other low-level programming usually does not have to be used. There is normally a software bug where user input is supplied to the application, and then it is processed by an underlying shell interpreter, where that shell interpreter executes whatever data it was given. Which if an attacker controls that data, you can supply operating system commands and gain full access to the system, which, as you can see in this picture here, we have a TrendNet system, and there are several HTTP post requests being sent to it, which then results in a network shell, which you can see we have root level permissions. So that was a full compromise through a command injection vulnerability. So testing for command injection. If you don't have source code, the biggest thing you can do is look for application features and functionality that would most likely call underlying system components. A big example would be ping or trace route or any mailing functionality where email can be sent. Really anything that could interact with the underlying operating system would be a good place to check for these types of vulnerabilities. Some test examples listed here for both Linux and Windows. The biggest one being command substitution, the bottom one. And you'll see this mostly on Linux systems, Linux IoT systems, where an attacker can utilize command substitution to get his injected command to execute before the developer's intended command, using either the backticks or the $parenthesis command parenthesis. So command injection countermeasures. Developers should avoid calling shell commands when possible. Stay away from functions such as system or exec-ve. If an API does not exist, so whatever you're trying to do, there isn't already an API for it, sanitize user input. Only accept input from a user that you are expecting to use in your application before passing it to a function. That's essentially a whitelist approach to where you have to have a list of data, and if supplied data does not meet that list, then you reject it outright. So an example below in Python, is using the os.system method to get a directory listing. And that is doing it by executing the ls command plus dir variable. Now, if an attacker supply a malicious value to dir, they could execute arbitrary commands. Clearly here the developer wanted to list the directories for the user, so a safe way to do that would be to use a built-in API, such as the list_dir method of the OS module, where only a directory can be passed as an argument, and if it isn't a directory, you'll be given an error. So that's a safe alternative that essentially resulted in the same thing for the developer, where they wanted the directory listing and they got the directory listing. All right, so buffer overflows, my absolute favorite vulnerability.
So Jacob, I had a question.
Go ahead.
So you discovered a vulnerability in IoT device this year and you presented it, and also you saw so many other vulnerabilities in various other devices getting presented. It will be great if you could also give a few, share some of your experiences in terms of like where buffer overflow was used, like Google Nest, when they got broken, this vulnerability was used, or some practical insights if you could share along with sharing these details. That will be very interesting.
Yeah, absolutely. I actually kind of touch on some of that a little bit later in the presentation, so I'll get to that in a bit. So buffer overflows, we've talked about them briefly, but they occur when a program attempts to write data to a fixed length buffer in memory and consequently overwrites the adjacent memory, which will result in a segmentation fault and the program crashing, which you can see in this picture highlighted in yellow. The program received SIG-SEGB, which is a segmentation fault because it received or attempted to execute data at an invalid instruction, which happens to be 444444, which is all Ds. That's the hex representation, which means input I supplied to the program basically interrupted the program flow and caused a crash, and now I am able to control what the program does. So testing for buffer overflows, pretty straightforward. We talked about it, dynamic and static analysis. Dynamic analysis, again, is the fuzzing, where you're sending a bunch of peculiar input to the program, speaking its protocol, and observing the responses. Static analysis would be source code review, going through source code, identifying possible vulnerabilities, and then performing some level of dynamic analysis to see if you can actually trigger the vulnerable code path. So countermeasures for buffer overflows are pretty straightforward, but honestly, they are overlooked a lot, especially in IoT devices. Developers don't use unsafe functions. If you are going to use them, or regardless, you should always perform bounds checking, which again is just ensuring that the data you're copying to a region of memory is within the allocated size. And then compile and link with overflow prevention techniques. And that would be using canary cookies, which puts a value in memory, and if that value is corrupted, the program will halt execution. ASLR, also known as address space layout randomization, which basically prevents an attacker from knowing where code is loaded in memory, and then data execution prevention or non-executable. And that marks the stack non-executable by default, meaning that code that is put into the stack region of memory for a function cannot be executed. It can only be used as a data reference point. So really quick, we're going to get into a buffer overflow demo. I'm going to quickly demonstrate an overflow in the ASUS WRT firmware on the ASUS RT N5 6U router. This overflow affected all ASUS routers. It has been patched in some of the models, I believe, but not in every model. And this exploit is specifically for the RT N5 6U. So I'm going to go over to my Linux machine, which you guys should now be able to see. Vikash, are you able to see my Linux machine? Can you guys read my screen?
Yes.
Okay, great. So what I'm doing here is I'm setting up a netcat listener on port 31337. I'm essentially waiting to receive a connection on that port. And now I'm going to run my exploit code against this ASUS router. We're fingerprinting the router now. As you can see, the target system was found in the signature list. It is an RT-N56U, and now it's asking us if we would like to use authentication. We're going to say yes. This is an authenticated buffer overflow exploit. But what's great about this vulnerability is that while it requires authentication, used in conjunction with an authentication bypass present in this router, an attacker can bypass authentication to exploit this buffer overflow and assume full administrative control. Now, I'm not going to demonstrate the authentication bypass today, but the router will give you both the username and password by requesting a certain application page. So assuming that we utilize that vulnerability to get the username and password, we're going to input them now. And once I hit enter up here, you should see at the top of the screen we receive a connection. So as you can see, the exploit launched, and up here we got a connect from me from 192.168.1.1, which is that router. So if we do a uname-a command, you can see that we are now on this MIPS system, and we control the system with root level privileges. There's the shadow file. At this point, the attacker, me in this case, can do whatever he or she wants. I completely own your router. I now can control all ingress and egress network traffic from your network, which means data coming in and out is subject to manipulation by me. I can poison your DNS, so when you go to Facebook.com or your bank, PNC.com, CapitalOne.com, you go to a malicious website where I then can attack other systems on your network, steal your credentials or other sensitive data. So this is a serious problem with with ramifications that I guess that you can't always quantify. Because this is something that is always severe, but in some cases it's more severe than others. All right, so continuing with the presentation, I just showed you a remote code execution vulnerability, and if that terrifies you, then mass exploitation most definitely will. So just imagine that you have a vulnerability or an exploit like I just demonstrated rolled into a software package that contains several other vulnerabilities for other devices that could run on its own. That's, in essence, a worm. And I wrote a piece of malware that I call the N.A.S.ty worm, which exploits 3 network-attached storage systems, hence N.A.S.ty, the D-Link DNS345, the Trinet TN200, and the Western Digital MyCloud. This worm that I wrote, basically you run it and it looks on the internet at different IP addresses for a open TCP port 80. If it's open, it attempts to fingerprint it, kind of like the Python code did that I just ran for you. If the fingerprint returns true and says, hey, I am one of these vulnerable targets, the worm will exploit the target. Once the new victim has been successfully exploited, the victim downloads and runs a copy of the worm code, and then this whole process rinses and repeats. So that remote code execution vulnerability can actually be turned into an automated a piece of attack software that goes out and finds all these vulnerable systems for the attacker and then exploits them. So the attacker isn't having to manually find these systems on their own. So this is a very, very, very serious and critical problem, as it will allow an attacker to gain access of many, many systems. And some similar occurrences would be like the Linksys moonworm, for instance. This was a self-replicating piece of malware that bundled a Linksys vulnerability or a couple of Linksys exploits into the software package that then exploited the vulnerability in several different Linksys models on the internet. And as you can see here, this picture from BBC is talking about hackers taking control of a little over 250,000 home routers, and that was the result of the moonworm. So just imagine if you had the power of 300,000 systems. The types of attacks that you could perform are absolutely devastating. I mean, you could definitely bring down parts of the internet infrastructure. As Dan Geer said in his Black Hat USA 2014 address, the Lizard crew using, I think it's the Lizard crew, using a tool called the Lizard Stressor, they brought down the Sony PlayStation Network and Xbox Live Network, over Christmas and New Year's by compromising a bunch of home routers and other IoT devices and launching a large and successful denial of service attack against these websites. So we're seeing real live examples of this in the world, and starting to be able to quantify both the gain that the attacker receives and then the losses that are occurred by the organization that suffers these attacks. Another big thing in recent news would be the shell shock vulnerability. Well, QNAP makes network storage systems, and their systems were vulnerable to the shell shock vulnerability, and a group of hackers wrote a shell shock exploit for these QNAP systems, rolled that into a self-replicating piece of malware, and started assuming control of the devices. And a final example would be the Synology ransomware called SynLocker. What this piece of malware did was exploit a vulnerability in a Synology service, and then basically encrypted the entire file system and all of the data protected by this network storage system, and was requiring users to pay some sum of money before the attacker would give them the decryption key so they could retrieve their stolen data. So that definitely has some detrimental effects on an organization or any user who is affected. So now we talked a lot about vulnerabilities, the exploitation of the vulnerabilities, how developers can prevent against them. We talked about threat modeling, which is used both in the designing of a system and then the audit of a system. Let's talk about, let's talk about some of the design principles that should be leveraged by an organization while developing a software product. So the first thing we'll talk about is least privilege, also known as the principle of least privilege. And this basically refers to the principle that a process or a piece of code or some task that is being executed or ran for a purpose on the system should be executed with the lowest level of privilege required. Meaning, if you were just, I don't know, creating a file on the file system, that file probably doesn't need to be created with root privileges, so you could create it with a lower privileged user. Another example would be running your web server as the built-in web server user, like Apache user, instead of root. So if the web server was compromised, the attacker automatically doesn't have full control over your system. While they do have some level of access, that is still something definitely to be concerned with. You aren't immediately left in a state that allows the attacker to do whatever they want to your system, which could result in you being instantaneously locked out. Secure by default. A system, it's secure. Basically, you can think of secure by default being if a system has a bunch of security options, such as a firewall or packet inspection, really anything you can think of. It is secure by default if it's in its most hardened state out of the box, meaning that a user doesn't have to go into the configuration and turn on security settings. They're already enabled. Failsafe, basically, if a system fails, you want it to fail in a secure state. You don't want it to fail wide open. A classic example of failsafe would be an electronic lock. If you have an electronic lock in your building and the power goes out, you want that lock to fail in a locked state. You don't want it to unlock if the power goes out. That would be a vulnerability. So failsafe, you can think of it as, all right, I have these protections. If I were to lose power or some other unexpected event were to occur, am I still going to be just as safe as if the system was operating as expected? Defense in depth. This is a big one that we hear in the security community, and this basically is a tiered approach to security. I mentioned it earlier with the cross-site request forgery attack and countermeasures, where you could use refer checking in conjunction with anti-CISO tokens in conjunction with re-authenticating users prior to a state change. This basically takes your assets and protects them with various layers of, or various tiers of protection. And if one tier were to fail, then the entire system will not be compromised. You still have one or more, hopefully more, other tiers that provide you with some level of protection. So you're able to come in, with your threat model and respond to any incident accordingly. And then finally, audit. Audit is absolutely critical. You need to have some level of accountability. You need to be able to review log files to see who accessed data when, how the system is being used, basically anything that will yield the administrator or operator of a website or system information about what's happening internally is both beneficial to the system operator and then the users, as it can help in debugging issues that an end user may have, but it can also help the website operators respond to an incident should one occur. And then finally, trust model. We talked about threat modeling. Trust modeling is, I guess, a component to all of this, security design principles. It's a bit different, and what a trust model is that it clearly defines, I guess, all of the boundaries within an application, and it allows a developer to pay attention to improper assumptions that are made about security and permissions within the system. And here is a way, or like an example of how a trust model can be beneficial. Earlier in the presentation, I talked about missing function-level access control, where there were authentication and authorization vulnerabilities. A trust model hopefully would have allowed you to identify some of those issues early on in your software development lifecycle. And then with your threat model, you should then be able to go back and adjust and account for these vulnerabilities without incurring too much additional costs. So IoT integration, this is pretty much the end of the presentation. Basically, this slide here is just kind of rehashing every different subject I talked about today. The core things before implementing any piece of software into your network or system would be threat modeling. And this is definitely applicable to IoT devices. As I said earlier, you as an administrator or an organization, you don't have as much control over these systems as you would like. They're not a company-owned system. You can kind of think of them as more of a bring-your-own device type of system, whereas they are really never to be trusted, as you can't maintain them with a level of granularity that you could with, let's say, a full-fledged Linux or Windows or Mac OS system. And then your security design principles. Following these design principles, from the start of development all the way to each subsequent release cycle will allow you to keep your costs low while developing a very secure and robust piece of software. So these are two things that shouldn't be overlooked. They should be utilized by any development team looking to build new software, whether you're starting a new project or continuing an older project, and then any security company or security team looking to ensure that a system is adequately protecting assets. So, yikes, what can we do? We've talked about a lot of issues. We've demonstrated some vulnerabilities by reviewing source code, by executing exploit code. It really is kind of a hard battle, especially for consumers. The biggest thing that consumers can do are to harden your SOHO devices or your IoT devices. And basically what you can do to ensure that they're hardened would be to disable any functionality that you are not using, change your username and passwords, ensure that you're utilizing encryption, things of that nature. And while this isn't a wholehearted defense, it will at least thwart some of the less sophisticated attackers that in the security community we like to call script kiddies. And you really need to demand that vendors put more emphasis into securing IoT equipment. These systems a lot of the time come in a state that is against most of the security design principles, and that isn't beneficial to the consumers or even, I guess, the resellers as they have to deal with the ramifications of publicly disclosed vulnerabilities. And then vendors, we've talked about this a lot already, but you must abide by the security design principles. It is an imperative step to developing secure software and having a sound and robust software development lifecycle. You follow the coding best practices, and you need to have some level of patch management or update mechanism put into place that will allow these systems to automatically update their software, and that way vulnerabilities will be resolved as you address them, but it will then also allow for the more technical users to opt out of automatic updates. Because as it is today, IoT devices aren't updated. They're normally plugged in and kind of forgotten about, and vulnerabilities may get patched, and but if they get patched, that doesn't mean that they can't be exploited, because in order to prevent exploitation, users need to update them. So moving forward, IoT systems need to have a more concrete way of delivering security and system updates to users. So that's my presentation. That's everything I have for you guys today. Here is my contact information, access, or a link to my blog and GitHub. Currently, my GitHub only has a bunch of exploit code and some papers on it. I'm eventually going to be releasing my prototype of my worm there, probably by the end of the week. So if you're interested, that's where you can reach me. I guess now we'll open it up to questions.
Great. Thanks, Jacob. We don't have much of time, so we had a few questions. We'll probably skip most of them. We will discuss only on a couple of them. So one question is, so it seems that IoT devices are very much similar to any other devices or applications out there, but probably just that it's less secure. I mean, will you agree with that?
Yeah, I mean, I really do agree with that. Honestly, we talked about it a little bit earlier, Vikash, where we were talking about modern computer systems, and being secure in a way that prevents them from being exploited like they were, in the early 2000s and early 90s. Well, the IoT systems, is kind of like reminiscent of the past, whereas we're looking at these systems and we're able to exploit them in a way that hackers or attackers were exploiting desktops in the 90s and in the early 2000s.
Absolutely. Like history repeats itself.
Right, that's exactly right. These systems are failing to utilize a lot of modern day protections. So it's more monetary benefit for an attacker to go after these IoT systems than it is for them to go after a Windows or Mac desktop, for instance.
Yes, yes. So I have one question here. So since hacking of IoT is easy and also the IoT companies are a lot younger and many of them don't have such security practices and maturity in terms of developing secure products, what do you think is the approach to recover from an attack and also patching? Because patching sometimes might be hard, right? So what's your thoughts on recovering and patching?
So, I mean, recovering really, I mean, it comes down to your incident response plan, and how you can kind of quarantine your network. But I guess specifically, I'll try to address IoT devices. If you determine that a breach was a result of somebody exploiting an IoT device, there are several things that you would need to do to that device. One, you would need to perform some level of forensic analysis to determine, how they got in, if the device is still compromised, did they compromise your data, did they compromise the device, talk to any other system on your network. And once you've kind of gathered your initial information about the breach, you definitely just need to get rid of that system completely. It needs to be retired from your network and it needs to be decommissioned. And I say that for multiple reasons. If anyone is familiar with BIOS-based attacks or bootkits, to where you're compromising the BIOS, so the very first instruction that the CPU runs is attacker-controlled code, there is no way you can ever trust that system again, because even if you were to try and flash the firmware, the code that would be doing the flashing would be malicious code, which means that the system is, in essence, bricked indefinitely. And that's kind of how these systems are. If you get access to an IoT system, I mean, you're running with the highest level of privilege, and you, in a sense, can change the firmware. You can modify it in any way that you see or you find necessary, and it can no longer be trusted. Because if you attempted to flash the firmware or make any change to it, I would be the one, doing that action for you, and I'm malicious. So the device is no longer trustworthy. So yeah, I hope that kind of answers the question.
Yeah, great. And this will be the last question. And before I ask, one disclaimer, quick disclaimer. I founded a company which does on-demand dynamic application security testing. We just got called iViz, which just got acquired by Cigital a while back, a few months back. Mm-hmm. So now back to the question. So that is, personally, I typically tell, like, if you can do both static and dynamic, that's the best. Both has its own pros and cons. So combining both together gives like the best result. Now the question which we got is, if you have to do either static or dynamic, like you might have constraints in terms of time or money, which one should you choose?
If I had to do either, I mean, that honestly is tough.
I know it's a tough question.
It is definitely a tough question. Okay, so I mean, I can come up with pros and cons, for the argument.
But if you had to choose one, which one will you choose?
All right, don't hold me to this, but if I were to choose one right now on the spot, I would definitely say static analysis. Assuming that you're even contemplating static versus dynamic analysis, to me, that's indicative of you being able to, afford the cost of static analysis, and therefore you should take that route, as it's going to allow you to get very close to that 100% code coverage.
Okay, so interestingly, I differ, and I'll tell you why. So this is a fun question. It came up. I thought I should give the disclaimer and ask. So I believe dynamic first. The reason is, I mean, it's not just for maybe if it is IoT and if you have access to the system, etc., it's different. But if it is a like normal web app, I believe dynamic first, because it's very easy, lesser of a cost, and a hacker is going to do that. I mean, the hacker might not have access to the code, so do the one which the hacker is going to do first. And this other couple of things is, one is there's typically more false positives in static, but the bigger reason is that the business logic flaws or the logical flaws are very hard to find from static. You can't get that. Whereas a hacker, without even having access to code, can find out those logical flaws. So the logical flaws are out there, accessible to a hacker, but very difficult in static to find. So that's like my philosophy, but I agree with you that there are coverage challenges, and also it has its own pros and cons. And I think it's a debatable question, but it's a fun one.
Yeah, absolutely. I agree. I mean, I'm pretty sure I could argue on either side of the offense for hours. So.
That's right. Yeah, that's great. So, Jacob, this was fun, very interesting, and I would like to thank you for the great presentation. And before we close, those who are out there until now, when you close the session, you will see a small questionnaire on CISO Platform Index, and the idea is, the idea with which CISO Platform came up with this is that as a community, if we share our experiences of using a product and how good it is, instead of somebody else telling us that this product is good or bad, if all the users of security products come and share their experience and rate the product, that's probably the best way to know which one to choose. At least it gives a good indicator. We have the opinion from certain community. If we can also get the opinion of the user community, that will be a great value add. So for the community, it will be great if at the end of the session, when the screen pops up, and if you find that, if you could just name a product, security product that you used, and how do you rate that. This information will be utilized later. In the middle of the year, CISO Platform will come up with a consolidated report on the user rating of the various products, and those who kind of vote for some product and rate a product, you all will get a free report. That's what I had been told. So I just wanted to convey that. So thanks everybody, and look forward to have all of you might be in the next session. Thank you, Jacob.
Yep, thank you guys. Thank you for having me. And if anyone has any additional questions, feel free to reach out to me on Twitter or LinkedIn. I'm readily willing to participate in the community. So if you have any question about exploitation, defense, secure development, reach out to me, and I'll be willing to help. Thanks a lot.